Hello, I'm Tom Buchholz. Welcome to this presentation, Gravitational and Dark Matter Concepts that can help explain and predict cosmic data. This talk includes an introduction, develops methods and results, discusses details and future opportunities, and includes concluding remarks. Introduction. This talk addresses, among other questions, the following two questions. Does the rate of expansion of the universe associate with two-body gravitational interactions between galaxy clusters? Might dark matter feature 5 new sets of elementary particles, with each set being much like the set of known elementary particles? Before we address those questions, we provide some perspective. More than 1,800 years ago, cosmology placed the Earth at the center of a spherical shell that contained the trajectories of objects such as planets and stars. Eventually, people moved away from Earth-centric cosmology. Around the year 1750, people began to speak of the Milky Way galaxy as an island universe. In 1920, the one galaxy paradigm was still prevalent. By the year 2020, cosmology suggested a 13.7 billion year timeline. For an era that encompasses much of the first billions of years, neighboring galaxy clusters moved away from each other with typical velocities of moving away from each other that decreased with time. For an era that includes the most recent billions of years, neighboring galaxy clusters moved away from each other at rates that increased with time. People suggest unresolved details and possibly other problems with concordance or lambda CDM cosmology. Lambda associates with some uses of general relativity. CDM denotes cold dark matter. In this talk, we explore the notion of a so-called multing plus IDM cosmology. Multing features so-called multi-tier Newtonian gravitation, not general relativity. IDM denotes a notion of isomeric dark matter, which tends to be more specific than CDM and to have some similarities to CDM. Newtonian gravity, Coulomb electricity and magnetism, Lorentz invariance and special relativity, and some verifications of predictions based on general relativity predate 1920. After 1920, people confirmed the existence of galaxies other than the Milky Way, discovered that most galaxies move away from the Milky Way galaxy, discovered phenomena that might associate with dark matter effects, and discovered that the rate of expansion of the universe is increasing. Dark matter associates with gravity that does not seem to associate with ordinary matter. Notably, perhaps based on the early successes of general relativity, people may have de-emphasized reusing, regarding gravity, aspects that associate with electromagnetism, the motions of charges within objects, and Lorentz invariance. Our work features such aspects. Open physics opportunities include the following: explain rate of expansion phenomena, explain and predict data that associate with dark matter effects, list and predict elementary particles, list properties of objects. Modern discussion of properties of objects dates back to at least as far as to Newton and the question as to whether gravitational mass equals inertial mass. Our work offers insight and possible progress regarding each one of the 4 opportunities. Our work features positing explanations for seemingly inadequately explained data and reusing or paralleling already useful notions. Our approach toward an explanation for eras in the rate of expansion of the universe features multing or multi-tier Newtonian gravitation. Our approach toward explaining ratios of dark matter effects to ordinary matter effects features IDM, or isomeric dark matter. This slide lists some observed ratios of dark matter presence to ordinary matter presence. As far as we know, lambda CDM does not explain the first three of these ratios. We seek to explain the ratios. Lambda CDM does offer explanations for example, galaxies that are nearly all ordinary matter and galaxies that are nearly all dark matter. Methods and results. Regarding bases for gravitational models, one choice is Newtonian gravity. Some models can model sources of gravity as being point-like. Some models use multipole expansions to model sources of gravity as being spatially distributed. Multing features the notion that a source of gravity can model as having sub-objects that move within the source. We will discuss notions that, for multing, monopole, dipole, and quadrupole contributions to gravity associate respectively with pull or attraction, push or repulsion, and pull or attraction. Our discussion of multing associates with two-body gravitational interactions between an object A and an object P. We aim to extend Newtonian gravity beyond its original emphasis on monopole interactions. Regarding the rate of expansion of the universe and interactions between galaxy clusters, we explore notions that quadrupole pull, attraction, started the early universe multi-billion-year era of decreases in the rate. Dipole push, repulsion, started the present universe multi-billion-year era of increases in the rate. And monopole pull, attraction, might start a future era of decreases in the rate. This slide reviews the familiar Newtonian force equation. Notably, no notion of velocity appears in the right-hand side of the force equation. This slide depicts Newtonian gravitational effects of an object A, as in active properties, on an object P, as in passive properties, that model as point-like and are separated by a distance r. The familiar Newtonian force law pertains. No notion of velocity appears in the right-hand side of the force equation. This slide depicts an aspect of multipole Newtonian gravity. Here we split object A into two objects, each of which has a rest mass of 1/2 the mass of object A. Each one of the two objects is farther away from object P than was the original object A. Thus, the dipole contribution to gravity dilutes the monopole pull, or attraction, and can associate with a notion of dipole push, or repulsion. This slide depicts another aspect of multipole Newtonian gravity. Here, again, we split object A into two objects, each of which has a rest mass of 1/2 the mass of object A. In this case, the dipole contribution to gravity can associate with the notion of dipole pull. We suggest that notions of spatial dipole distributions would, at best, lead only statistically to net dipole push. We look for another mechanism that can underlie dipole push. We consider aspects that associate with the motions of subobjects of objects, and we consider aspects related to Lorentz invariance. Regarding Lorentz invariance, modeling features the position and properties of object A at a previous time at which object A crossed the light cone that associates with object P. Also, discussion of some aspects shifts from masses to rest energies and kinetic energies, but not necessarily to potential energies. Suppose that object A moves relative to object P. In Newtonian gravity, The gravitational effect on object P does not change. However, in the context of Lorentz invariance, object P measures object A as having more energy than in the case for which object A is at rest. The additional energy might associate with more monopole pull, but the momentum-related current of object A energy contributes to monopole push that balances out the motion-centric component of monopole pull. We consider that a cosmological object A, such as a galaxy cluster, can contain subobjects, such as galaxies, atomic nuclei, and electrons, that can move relative to the center of mass of object A. We are about to consider that Lorentz invariance can pertain regarding, for example, aspects pertaining to the motions of galaxies within galaxy clusters. This slide repeats a previous slide that associates with zero motion of subobjects of object A. Suppose that object A does not move relative to object P, but subobjects of object A do move relative to object P. Paralleling notions that associate with electromagnetism and magnetic moments, the gravitational field effects associate with dipole. For gravity, the dipole effects associate with push. Suppose that the distance between object A and object P is adequately small and that the two objects are not colliding. The overall gravitational effect on object P associates with push away from object A. This slide redoes the previous slide to emphasize the notion that we are discussing interactions between objects that can meaningfully model as point-like. The total kinetic energy of subobjects of object A associates with being a property of object A. For galaxy clusters, the total kinetic energy of subobjects usually associates mostly with the thermal energy of the intergalactic medium and not all that much with the motions of galaxies. More generally, adding a tier, in other words, adding 1 to the number of occurrences of the prefix sub-hyphen, associates with diluting effects that associate with the previous tier. Monopole associates with pull, dipole associates with push, quadrupole associates with pull. We turn our attention to dark matter. Regarding IDM, we posit that nature includes 6 near copies of the set of known elementary particles. Each one of the 6 so-called isomers associates with its own electromagnetism. One isomer underlies ordinary matter stuff. 5 isomers underlie some, but not necessarily all, dark matter stuff. Various types of variations between isomers are possible. This slide indicates that one change regarding a mass of an elementary fermion would associate with ordinary matter stuff behaving like dark matter. The chart suggests a pattern regarding the masses of the 3 charged leptons and the geometric mean masses for the 3 generations of quarks. If one assumes a rest energy of about 8.5 million electron volts associates with the empty would-be lepton cells, each one of the 2 logarithms of masses columns exhibits a nearly uniform spacing of the logarithms of masses. If one assumes that the F equals 1 or flavor 1 charged lepton associates with the K equals 1 mass and not with the K equals 0 mass that associates with the electron, the stuff that would have associated with protons would associate with neutrons that would not decay. There would be few, if any, atoms. There would be few, if any, freely roaming charged objects. This slide extends notions from the previous slide. The slide presents a candidate IDM, or isomeric dark matter, description for 6 isomers. One isomer underlies ordinary matter. the concordance cosmology three-word term cold dark matter approximately characterizes the stuff that associates with the other 5 isomers. Other, similar specifications for 6 isomers are possible. Our work features aspects that go beyond the 2 featured questions. This formula links the ratio of the mass of the tau lepton to the mass of the electron to the ratio of electromagnetic repulsion to gravitational attraction for 2 electrons. A set of formulas links the properties of the known elementary bosons. The relationships among the masses of the W boson, the Z boson, and the Higgs boson might extend notions related to the so-called weak mixing angle. Discussion. Some people interpret some recent data as pointing toward a future rate of expansion era that we would say features monopole attraction. Lambda CDM cosmology seems not to suggest such an era. Multing plus IDM suggests possibilities for such an era. We suggest that multing plus IDM and general relativity complement each other. Multing might provide an approach to the rate of expansion of the universe that is less dependent than uses of general relativity on parameters such as an equation of state. General relativity provides a basis that is better than multing for understanding collisions and mergers of cosmological objects. This slide suggests possible bases for the plus in the 5+1 ratios of dark matter effects to ordinary matter effects for many galaxy clusters and for densities of the universe. More than one of these or other possible bases may pertain. Regarding narrowing the class of IDM candidate specifications for dark matter, attention to data, including data about collisions of galaxy clusters and data about galaxies, might prove useful. Our work might help support notions that one can avoid thinking of space-time as a thing that associates with properties such as curvature. Perhaps space-time is to gravity as ether is to electromagnetism. Such thinking might lead to somewhat straightforward paths toward developing theories of quantum gravity. This slide recaps and points to opportunities that span the categories of future observations, experiments, models and modeling, and applications of physics theory. Our work suggests many possible future activities, but does not necessarily suggest when people will be able to carry out the activities. We experimented with using online services that have bases in artificial intelligence to do relevant computations. We report some of the results with a caution that AI and users of AI can make mistakes. We fed one prompt to each of 4 services. The prompt left considerable latitude for how the services might do their work. Regarding the rate of expansion of the universe in general, and specifically the Hubble parameter h of z, the slide shows one of the 4 results of asking the services to determine how far back in time data is reliable, and then to provide 3 sets, data, lambda CDM estimates, and multing plus IDM estimates of results. Across the 4 services, our work seems to be more accurate than lambda CDM. However, even if one accepts the calculations, one might explore notions that the amount of better accuracy might not be all that significant. Conclusion. We use seemingly straightforward methods. We produced explanations and predictions that span various aspects of physics, including the rate of expansion of the universe, dark matter, elementary particles, non-monopole gravitational properties, and properties of galaxy clusters and galaxies. We suggested insight and future activities regarding each of the 4 long-term opportunities that we identified near the start of this presentation. We suggest that our work suggests complements to, variations on, and alternatives to some aspects of lambda CDM cosmology. We suggest that our work might add impetus and means to explore the extent to which complements to, variations on, and alternatives to lambda CDM can prove useful. Thank you for watching this presentation, Gravitational and Dark Matter Concepts that can help explain and predict cosmic data.